Today I'll be proving that the determinant of a 2 times 2 matrix equals the area of the parallelogram formed by those the two vectors of that matrix. So without further ado, let's begin the proof. Let's say we have an A, a B, a C, and a 0. Sorry for my coughing. So what would this look like? Well, this would be A0, right? And let's say BC is someone here. This would be BC. Okay. And then dot, dot. Here's the parallelogram formed. So what is the area of this parallelogram? Well, it's going to be, area is going to be base times height, right? This would be height, and this would be base. Well, we know that, let me remove that. Area equal base times height. Well, we know that A is the base, right? Because from here to here is A. And we know that C is the height, because from here to here is C. So AC. And look, that also equals the determinant of A, which also equals that A. Alright? Because that A equals AC minus 0, which also equals this. But the problem is, what if we rotate this parallelogram? Okay, so now we're trying to find the matrix formed by A0, BC, and we multiply it by a rotation matrix. So cos theta, sine theta, negative sine theta, cos theta. Alright? So what happens when we do this? Well, when we rotate a parallelogram, the area will stay the same. Area will still equal, well, BH, or in this case, it would still equal AC. But what about the determinant? Would the determinant stay the same? Well, let's see. So let's find the determinant of this thing right here. That would be cos squared theta, because cos times cos, minus negative sine squared theta. And this just equals 1, which equals det rotation. Alright? And the determinant of these two matrices multiplied together, so det AB would equal det A times det B. And we figured out that det rotation, or det B, equals 1. So it'll just end up being det A again. So look, if we rotate this, this parallelogram, the determinant stays the same as well. So if we rotate this parallelogram, the area stays the same, the determinant stays the same, hence the determinant will still equal the area. Now, the last thing I need to prove is that the combination of these two matrices spans the entire R2 space. So I want to prove that this matrix with one of its legs on the x-axis multiplied by a rotation matrix includes all the parallelograms in this space. So it could be a parallelogram here, parallelogram there, and so forth. And here's how I'm going to do that. So first, let's just multiply these out. We get that A cos theta plus B sine theta. And down here would be just C sine theta. It would be a 2 times 2 matrix. So, and then we have B cos theta, or negative A sine theta, plus B cos theta. And at the bottom here, we would have C cos theta. Alright, now I need to prove that we can vary theta, we can vary A, B, and C. Now I need to prove that the set of these two vectors spans R2. So how would I do that? So first, I need to prove that whatever value this takes the value of this in a sense, does not depend on the value of that. So like, let's say c sine theta equal 1,000. I can make c cos theta equal 1. So how do I prove that? Well, the proof is actually pretty simple. All right. So let's take this example. In this example, we can make c equal like 1,000. Hold on. How do I do this? Let's just make it. All right. I'm not gonna try to do the math here, but basically, we can just set c to around 1,000 and set sine theta to around 1. So 1 times 1,000 would be 1,000. Then if sine theta is around 1, cos theta has to be a really low number. So a really low number times 1,000 would approximate around 1. So we know that any combination of numbers like 1,001 or negative 500 and 450, these combinations of numbers can be met by c sine theta and c cos theta. So we know that in a sense that this number here does not depend on that number there. In a sense, all right? And then now we need to prove that this term here does not depend on that term. So let's say we decided on a value of theta and a value of c. So that means cos theta and sine theta are constant and c is a constant. So we can just do a matrix here where this is A and this is B, and we look here, it's just cos theta, sine theta, negative sine theta, cos theta. And this matrix right here is an independent matrix. So this matrix spans R2. Because these, no matter what value of theta, are going to be independent columns. If they're independent columns, then they span R2. And remember, A and B are still variables. We decide what C and sine theta, so we assume cos theta and sine theta and C are constant, but A, B are variables. Now, if this row is a constant, this row is a constant, however, these constants are independent to each other, and these are variables, then this spans R2. Or in other words, this here, this entry, in a sense, does not depend on this entry. So this entry can take on a value of like a random value 1,500, and this entry can take on a value of 500. All right, I hope that made sense. Let me see if I made any mistakes. All right, yeah. I don't think I made any mistakes. The hardest part to prove is that c sine theta and c cos theta can be whatever they want to create whatever vector they want. Hopefully you can see why that c sine theta can equal anything and c cos theta can also equal anything. So if we were to write c sine theta, c cos theta here, this vector would span R2 as well if we can vary theta and c. All right, so this would span R2, and then furthermore, if we assume that cos theta and sine theta are constant, these are independent vectors, and AB are variables, then this also spans R2. So that means each 4 of these entries can be whatever they want. And so if all of these 4 entries can be whatever they want, then every parallelogram in this R2 space is covered by a rotation and a parallelogram with one of its legs on the x-axis. Thank you.